So this section is about these trigonometric identities, Ben. So let's have a look at them. Ben? Here we are. What I want to do is show how this first one's arrived at. So I just want to focus on these. These identities, and here's one, tan theta is sine over cos theta. They're arrived at from what we know about angles so far. So you have had defined to you before, to do with a right angle triangle, the sine is the opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If we write what sine theta over cos theta is, that's this bit here, then that will be opposite over hypotenuse, because that's what the sine is, opposite over hypotenuse, divided by adjacent over hypotenuse, because that's what the cosine is. But if you know that if you divide fractions, if you divide one fraction by another, you invert the second fraction and multiply. That's what I've done here. The bottom fraction I've turned into h over a and multiplied. Now if you look at this, the hypotenuse actually cancels, and that equals opposite over adjacent, which is the tangent. So in other words, we've proved that sine theta, therefore sine theta over cos theta, equals the tangent of theta. And that's the first trigonometric identity. So it's arrived at by looking at what we know about angles and then seeing what else we can find out. And here's the first thing that we use. Sine over cos is tan. Let's just have a look at one or two of the others. Because we use tan to the minus 1, for example, or sine to the minus 1, means the angle whose sine is theta. We can't use that for the inverse, so sine to the minus 1 theta not so, because it does make sense in English. Because sine to the minus 1 theta means the angle whose sine is theta, then sine to the minus 1 theta does not equal 1 over. We're used to, aren't we, the minus, the negative power meaning 1 over. In this case, it doesn't mean that. It means something else. It means the angle whose sine is. And you're used to using that button on your calculator. So we have to use something else to mean the inverse of sine theta. We use something else to mean the inverse of sine theta. Or sine theta, or cosine theta, or tangent theta. Well, that's stated above. Sine, the 1 over sine theta, we could write it like that. We could use 1 over sine theta, means the cosecant of theta. That's defined as, and if you look up here, you'll see it. 1 over sine theta is the cosecant of theta, often abbreviated to just cosec. And that's how we say it, cosec. So what does cosec theta mean? It just means 1 over the sine of theta. Similarly, 1 over the cosine of theta is written as the secant of theta, commonly known as sec. So sec theta means 1 over the cosine of theta. And I could never understand why secant didn't go with sine and cosecant go with cos. That sort of makes sense to me, but it's the other way around, unfortunately. Okay? So cosecant goes with the sine and secant goes with the cosine. And then finally we've got 1 over the tangent, or 1 over tan theta, is written as the cotangent of theta. And we refer that cot. So we've got cosec, sec, and cot, and all that means is 1 over. 1 over the sine, 1 over the cosine, 1 over the tangent. So it's nothing fancy, just that. And so we now have these identities, look. Tangent is sine over cos. We've just shown that that's the case. We proved it. So cotangent, which we've just defined, remember, as the inverse of tangent, is cos over sine. So that's the second identity. And then we've got secant is 1 over cos, cosec is 1 over sine, and cotangent is 1 over tan. So those are the first identities that we use. And we use them to play around with and simplify expressions involving trigonometric ratios, as we'll see. Okay. Let's use Pythagoras to prove another identity. Yeah, there it is, right angle triangle. A squared plus b squared equals c squared, Pythagoras. If we take this formula, a squared plus b squared equals c squared, and divide by c squared, we get a squared over b squared plus b squared over c squared equals c squared over c squared. We divide everything by c squared, Gareth. So we're not square rooting yet. If we wanted to find it, we'd have to square root at the end. Oh, sorry. Well done, Tommy. I don't know what I'm doing here. It should be dividing only by c squared, aren't we? A squared over c squared plus b squared over c squared equals c squared over c squared. So long as we divide every term by something, we can do anything we like to this equation, or this formula. So that's perfectly acceptable. C squared divided by c squared is 1. And instead of writing a squared over c squared, we could write a over c all squared plus b over c all squared equals 1. Couldn't we? Okay. Now if we look at a over c, the cosine, to do with this angle, look, a is the adjacent to the angle, c is the hypotenuse to the angle, so that's to do with cosine. So instead of writing a over c, we could write the cosine of theta. So therefore, the cosine of theta squared, note the way we write that, cos theta squared. If I want to show that the whole thing is squared, I would just put a little 2 here by the cosine, cos squared theta, plus, how could I write b over c? What does b over c equal? In terms of theta, b is the opposite, c is the hypotenuse, sine. So instead of writing b over c, I could write sine, but it's squared, so sine squared theta equals 1. And that is one of the most used trigonometric identities. So there's another one. So from Pythagoras, which we know to be true, from our knowledge of the sine, cosine and tangent ratios, which we know to be true for a right angle triangle, we can then rearrange the formula and end up with something else, which we've now proven to be true. So we can now say that the cosine of an angle squared plus the sine of the same angle squared is 1. So let's try that on the calculator and see if it works. Let's try the cosine of, say, 30 degrees, and then square it on your calculator, plus the sine of 30 degrees, and then square it, equals, and you should get the answer 1 because of that identity. Okay, so we've come up with something that is true from a knowledge of other things that we know that are true. And actually, that's the way maths builds. We start from something that we know that is true and then find out other things that can be shown to be true from it. Prove other things that we can then use. If I go back to this, a squared plus b squared equals c squared, Tom, if I go back to here, and instead of dividing everything by c, I were to divide everything by b, I'd end up with another identity. If instead of dividing by b, I divided everything by a, I'd end up with yet another identity. And if you look at the textbook and you're interested, you could find out 2 more trigonometric identities that we can prove from Pythagoras. So Pythagoras actually gives us 3 trigonometric identities, but I just wanted to show you one of them. And there it is, cos squared theta plus sine squared theta equals 1. And that's the sort of one, if you do this sort of thing, you get to know it. Okay. So those are some trigonometric identities. Now there's another one that I want to show you, or another 4 that I wanted to show you, and that's these. Compound angle formulae. These can be shown to be true, and if you're interested in the proof, it's taken from just constructing right angle triangles. You can prove these formulae work, and I've put the proof on the site as on a separate handout, so if you wanted to have a look at that, you could see how it's calculated. But it's a similar sort of way. This is the use of Pythagoras and the sine, cosine and tangent ratios that you know already. So from those, you can prove these are true. I'm not going to go through it, but if you're interested, you could have a look. All you need for the purposes of this course is to know what they are. Not to remember them, but to have access to them. So there they are. They're called the compound angle formulae. So there they are, used to combine waves in AC circuit theory, which you may do in the future. So that's their application, or one of them, in engineering. So what does it mean? Let's just have a look at one. Let's take the first one. Sine A plus B equals sine A cos B plus cos A sine B. What it means is, if I take an angle, if I've got 2 angles, so the sine of, say, 30 degrees plus 40 degrees, so if I've got, say, the sine of 70 degrees, I could split that up into 30 plus 40 or 20 plus 50, however I want to do that. And it can be written as the sine of 30 degrees multiplied by the cosine of 40 degrees plus the cosine of 40 degrees multiplied by the sine of 30 degrees. That's what it's saying. For example, so if on your calculator you worked out what sine 30 times the cos of 40 is, and then added the cos of 40 times the sine of 30, that should equal the sine of 70 degrees from those compound angle formulae. Yeah, if I had 35 and 40, 40 and 35, that should be the same as the sine of 75, whatever combination. Ah, right. Well, that actually takes us to another identity if we do that. So hold on to that question, Gareth. If you want to just so you can demonstrate that this works by example, Tom, by looking at an example and show that it works, but we've not proved it by doing that. The proof would be to have a look at that handout that's on the website. But we can demonstrate that it does work. So Gareth just asked the question, what if the two angles are the same? So let's call them, it doesn't have to, 35 and 35 was one example, but it could be anything, okay? If the angles were the same. Write down what the answer would be using that top identity, compound angle formula rather, what sine A plus A would be. And I'll just pause while you... So let's look at this, sine A plus B, A plus A rather, that's going to equal sine A cos A plus cos A sine A. So if the angles are the same, we get that, it'd all be A. So can we simplify this right-hand side? Instead of writing sine A cos A plus cos A sine A? 2 sine A cos A, yes. And how can we simplify the left-hand side? A plus A sine 2A. And that is actually another formula that we can use. So the sine of 2A is 2 sine A cos A. And that's useful. If we've got a sine of an angle, then that's the same as 2 times sine of half that angle times cos of half that angle, if you think about it. So we could write it slightly differently and say, or we could write sine A equals 2 sine half A, or A over 2, cos A over 2. So hopefully you can start to see how we can write down all different identities, things that will help us manipulate angles just from that start point. And we can expand that idea and look at other identities, quite a few of them, but they all come from this sort of idea.